Hi guys, it's the Proof Architect here. Welcome to my channel. And now today I'm going to show you that imaginary numbers under multiplication form a cyclic group of order 4. Now, I'm trying to come this from the simplest approach as possible. So before I go and define those group theory terms, cyclic group and order, I'm going to go and talk about where imaginary numbers come from. So imaginary numbers come from the problem on how we define a negative number inside a radical, most common being -1 and a square root on top of it. We have no idea how to deal with this in the realm of the real numbers. Absolutely no idea what to do. So we're going to extend our realm of numbers into a bigger domain of numbers called the complex numbers, which are represented like thus. Basically any number, a plus or minus bi. I is the imaginary unit, the imaginary number, which this is defined as square root of -1 equals I. And a and b here are real numbers. Now, an interesting thing we can do now is multiply I by itself and see what happens. Because if it's true that square root of -1 equals I, then multiplying by itself square root of -1 times square root of -1 equals I times I. On the right hand side, since we have the same base, that just becomes an I squared. And same here, since we can represent square roots in terms of rational exponent notation, this is the same as -1 to the half times -1 to the half. So then you can add these exponents together. -1 to the half plus a half. And you get -1 equals I squared. Usually, I think in most classes, you usually learn up to there and then start with the multiplication. But let's do something a little bit interesting further. Let's go and multiply it again 2 more times. This is where the number 4 comes in handy. So I'm going to multiply -1 by I on both sides. I'll naturally get -I times I cubed. And then if I multiply it again, -I times I equal I cubed plus 1, so that gives me I to the 4 equals -I squared, but I squared, as we just saw, is just -1, so this is negative times -1 times I to the 4, which gives us back to 1. So the order 4, which I'll explain later, corresponds to how many times you can raise this imaginary unit I to a power before you end up back at 1, which is considered an identity element in this case. And just to show that it represents a rotation, which I'll shortly describe, if I multiply I again, I equals I to the 5th. So this is kind of the same thing as like multiplying 1 by I. Okay. Now, I mentioned that you can visualize the powers of imaginary numbers up to power 4 as rotations. I will claim that they're 2-dimensional rotations. And we can represent them in something analogous to a Cartesian coordinate diagram. Now remember, so let me write this out. We have 1 equals 1. We have I equals I. We have I squared equals -1. We have I cubed equals -I. And we have I to the 4 equals 1 again. Goes back to the same thing. You're familiar that the Cartesian coordinate graph is simply a graph with 2 axes, x and y, And you can draw a whole bunch of things on there, like graphs of ordinary functions in the high school algebraic sense, and vectors and other things. But these are assuming that x and y are real numbers. Well, the Argon diagram bumps this thing up by a notch, because now x is going to be a real number. So your horizontal coordinates or horizontal distance is going to be real numbers now. And the vertical component is going to be imaginary numbers. Basically this part of the complex number. And now using vectors, which in a pseudo-Euclidean sense are just arrows with direction and magnitude, I can represent these guys, these imaginary numbers, under the two-dimensional Cartesian coordinate, two-dimensional Argon diagram. Because, and now for some color, if this is 1, then this corresponds exactly to the complex number 1 plus 0i. There is no imaginary component. So we can write this out as the vector from the origin 1, 0. And if this is I, we only have the imaginary part, and the real part is 0. So this is the equivalent as 0 plus I. So we get 0, 1. Now we go to the I squared, which is rotating counterclockwise. By convention, when we do rotations, we always do counterclockwise. So we start here on the right axis and go counterclockwise. So we rotate again, we end up, you see the pattern now, negative 1, 0, because this is simply negative 1 plus 0i. And now here you end up with 0 plus negative 1i. And finally we have 1 plus 0i. You basically end back right where you started from. You complete a full cycle. So that's kind of intuitively why you call it a cyclic group. Without even going to group theory, I'm just explaining it purely in terms of rotations. And yeah, this is 0, negative 1. And now to go and explain, so in total I've shown you, intuitively speaking, through a visual analog, that the imaginary numbers under multiplication form rotation cyclic group of order 4. But now let me go and spell out what a group is, very quickly. So a group is basically the study of, not surprised, group theory, and it's just any basic algebraic structure that has these following 3 properties. So number 1, it must have an identity element. It must have an inverse. And it must be associative. Let me go and explain intuitively what these things are very quickly. An identity element means if you act on that object with the identity element, you get the same thing back. It's kind of like inverses, on the other hand. You can think of it as, if I perform this operation on this thing, it undoes what that operation does. Basically do the opposite of what you do. And if you multiply anything, say an element, by its inverse, you get back the identity element. Let me use E. This is Gaussian notation, and it doesn't depend on the order you do it. So the basic visual analog I always like to use is especially if you only know inverses from functions of inverse graphs, you can think of it like paper flipping. Like if you have a graph in the Cartesian coordinate, x like y equals x squared one another. You want to find the inverse? That's simple. You just draw a diagonal here, and then you flip it over. So it's kind of like paper flipping. It's like if I were to go and like crease this thing paper in half, the act of performing the operation is like folding it in half, and to do the inverse, it's undoing it. So I initially have a horizontal sheet of paper. That's the same. I have it. That's the inverse now. I end up with half a segment of paper. And if I do it again, voila, I get the same thing back. So that's how inverses and identities work. And then associativity just means that the way you group, the way you order things doesn't matter. I'm going to have to end it there because it's going to... I'll explain later the difference between associativity and commutativity. There are two different sets of ordering of stuff, which are very important. But all you just need to know is that this is a thing that you need in a group. So imaginary numbers form a group, and we can actually tie each of these four elements of the group to numbers. Okay, now I'm connecting to number theory now. I claim that the imaginary numbers of cyclic order 4 can map to Z4, which is the integer group of addition. Integer group under addition. Modulo 4, which is usually represented as this, Z4. And if you're wondering why on earth we have a Z as a symbolic notation, that's due to the German language. Fortunately or unfortunately, depending on what culture you come from, if you're a German, you're lucky, integer in German is written as Zahlen, as well as most other different kinds of numbers. Zahlen, something, Zahlen, blah, blah, blah. But we can denote the elements of this group as the following: 0, 1, 2, 3, and mod 4. And each of these guys, starting from 1 up to negative I, corresponds to these groups. So 0 corresponds to 1, the 0 equivalence class corresponds to 1, the 1 class corresponds to I, the 2 corresponds to negative 1, and the 3 corresponds to negative I. Okay. Oh yes. So now I should go and explain, like, what the heck is this congruence module now? It's basically just division, like the proper way of talking about how division works. And actually, you can represent it just by doing something that you learned since middle school or like pre-K school. Pie charts. Pie charts. Best way to think of division is just a circle, and then you're carving it up into different pieces. You can think of them as pie pieces or cake slices in this case. And you're making 4 slices. So you cut 2 lines and you end up with 4 groups. The stuff which is kind of unfortunately counterintuitive is where, wait, there's no 4. If I were to go and shape this up and represent the 4th element, or the entire pie, why the heck is there no 4 represented in this congruence class? That's a very tricky convention war that certain mathematicians and circles have been having. We've been constantly debating whether we start counting at 0, start counting it. Start counting at 0 or 1. And this has been the subject of some debate in certain circles nowadays. But I think the answer that fortunately or predominantly stands out is that when we define the natural numbers, the counting numbers, we say that the first element is 1. And yet, when we're dealing with number theory, congruence modulo, we start counting at 0. That kind of personally irks me, but we just have to deal with that. So you can think of it like a pie, but when you're looking at the group Z4, you have to start by considering, oh, I have a pan of pie and there's nothing in it. That's equivalence class member 0. Now if I fill in a slice, that gives me 1. If I take one slice of pie, that's 1. If I have 2 slices of pie, now it's 2. That corresponds to negative 1. And the previous one is I. If I take 3 slices, I get negative I. And if I fill it fully out, I get back 1 again. So, kind of weirdly, in Z4, there's no difference between a pie plate with nothing and a pie plate with something. Yeah, kind of weird, but I'm just stating the status of affairs on how imaginary numbers are constructed and defined underneath this framework. So now, the good thing about like mod 4 is that, or the reason why we have mod 4, is that we can then keep extending these rotations. Like, take a look at we agreed that imaginary numbers represent rotations in 2-dimensional planes, right? What if I want to rotate more than one revolution? What if I want to rotate 2, 3, 4, 5 incountable revolutions? Keep going on like forever, as how many as I can count. And I want to include all the possible integers, like I rotate this baby 6 times, 8 times, 11 times, -1 times, -2 times. You can do this if you understand number theory and apply congruence modulo. Because I claim that yet another way we can write this guy is equivalent to taking I and raising it to any multiple of 4. So 4k will equal 1. So k is basically an integer. If I take any imaginary number and raise it by a number that's a multiple of 4, 4, 8, -4, -8, 16, -16, you get the picture, and 12, etc., I will essentially end up with 1. And that's just borrowing from this class, because 4k here is just any multiple of 4, and you have 0 remainder. You get everything left, so this is a +0, which matches up with this guy. So that's where it helps us. And then I can do the same thing with the other elements. I to the 4k plus 1 equals I to the 4k plus 2 equals -1, and I to the 4k plus 3 equals -I. So everything is represented here. This guy too. And so there you have it. I've given, is that 4? Yeah, that's basically like 4 representations of how you can write in kind of like different languages in math, sub-languages of math, the imaginary numbers under multiplication. And the reason why it's called a cyclic group of order 4, is that if I multiply the imaginary numbers 4 times, then I end up right back at the identity element, which in this case would be this guy. This guy is the identity element, the 1, or in other words, this arrow. This is considered the identity element in our representation of the imaginary numbers. Hello everyone. As I mentioned in the how you can think of complex numbers as rotations around the Argon diagram, I kind of stated that you could rotate your complex number vector in either clockwise or counterclockwise directions. But I didn't state the reason why that is the case, of which I'm just going to quickly discuss right now, is because that complex numbers under multiplication is commutative. And here's basically a short way of showing how it's the case. Say I have arbitrary coefficients for the real and imaginary parts of two complex numbers, z1, z2. Then we just go and multiply them together, and I end up with some real part that's a real number, and an imaginary part that's a real number. I do the same thing here to this guy, and I get a real part here, I get my real part here, which is a real number, and my imaginary part here, which is a real number as well. Now, simply due to the commutativity of multiplication and addition in R, see, this is AC minus BD, and here is plus AD plus BC. Here I have CA minus DB plus CB plus DA. Can simply rewrite that into the same guy, AC minus BD plus AD plus BC. Therefore, Z1 times Z2 equals Z2 times Z1. So, complex numbers are commutative, and rotating in any direction is allowed. In case you're already savvy with group theory, I think there's some theorem that the integer group Zn under addition is simply cyclic and commutative. Those are two distinct parts. And this one I'm even more uncertain of, so let me know if this is a mistake, and I'll mention it. But I vaguely recall there's a theorem which says if the group is cyclic, then it has to be commutative. So if you don't want to bother doing this proof, or don't see it as an obvious fact, then you could appeal to this theorem as another way to show why we can rotate complex numbers in any direction. Okay, but yeah, that's it. That's basically it about the main basis complex numbers and how to understand them as rotations in two-dimensional space. I think in future videos going on, I will potentially go into a bit of a algebraic excursion. I might potentially cover videos on quaternions, which I know that 3 Blue 1 Brown has covered in great detail, which describes rotations in 3 dimensions. And then maybe even later on, we'll talk about octonions, which are a special class of algebraic entities that don't obey the law of associativity. So that's something kind of cute, and a side project I find I might do in the future. Also, just to follow up this video, there's a particular problem about raising powers of I, which I'll be putting on the channel up soon. So feel free to take a look at that when you have the chance. Okay, if you enjoyed this video, please feel free to like, comment, and subscribe. And until then, I hope you have a pleasant day.